The main function of astronomical telescopes is to increase the intensity of light that reaches the viewer, not to magnify the image, as stars would look like spots even when magnified. A telescope gathers incoming light, thereby increasing light intensity. Thus stars seem brighter, and even distant dim stars can be observed which are not visible to the naked eye. The light is collected by an objective, which can be a lens in refracting telescopes or a concave mirror in reflecting telescopes. The larger the objective is, the more light it collects. Thus, the telescope becomes suitable for observing more distant stars. For example, when the diameter of the lens is 10 times the diameter of the pupil, we can see stars that are 10 times further, and we can observe about 1,000 times as many stars. In Keplerian telescopes, there are two convex lenses. The objective lens refracts the incoming light rays, which then meet in the focal point and travel towards the second convex lens. The focal point of this lens is the same as the focal point of the objective lens. Thus, it refracts light rays so that they are parallel when they arrive at the eyepiece. Today, Keplerian telescopes are widely used by hobby astronomers. It is not suitable for terrestrial observation as it produces an upside-down image. In Galilean telescopes, there is a converging lens and a diverging lens. The convex objective lens refracts the incoming parallel light rays, which then travel towards the focal point but cannot reach it, as a diverging lens is placed in their way. This refracts them so they travel parallel to the eyepiece. The image quality of Galilean telescopes is not as good as that of Keplerian telescopes. Thus, they are rarely used for astronomical research. The main advantage of reflecting telescopes is that they contain large mirrors, which are much cheaper to produce than the large lenses in refracting telescopes. Therefore, the largest telescopes used in astronomical research are reflectors. In Newtonian telescopes, the primary mirror collects and focuses the incoming light rays. The light reflected by the primary mirror is directed towards the eyepiece by a secondary, flat mirror. The convex lens in the eyepiece refracts the light rays. They become parallel and reach the eye. In a Cassegrain telescope, the concave primary mirror contains a hole in the center, permitting the light reflected by the convex secondary mirror to reach the eyepiece. The Hubble Space Telescope is a Cassegrain reflector. In Nasmyth telescopes, the incoming light rays fall on a concave primary mirror, then are focused towards a convex secondary mirror. This reflects them towards a tertiary flat mirror, which then reflects the light to the eyepiece or an instrument. The advantage of this type of telescope is that there is no need to make a hole in the primary mirror, which can be difficult in the case of large mirrors. There are many other instruments used in optical telescopes. Moreover, not only visible electromagnetic radiation, or light, can be used for astronomical observations. With special telescopes, astronomers can also observe infrared and radio waves and microwaves, which have a longer wavelength than visible light, as well as X-rays and gamma rays, which have a shorter wavelength than light.